Kia ora. I just got my hands on the 2022 distributions paper for level 3 NCEA. So what I'm going to do is I'm going to have a little run through for you guys, just so you can check if you did this right when you were going through the exam. So question 1. It has been estimated that for a New Zealand clothing retail company, a purchase is made by 35% of customers entering their stores. Straight away I'm given a probability. It's looking like binomial. Using an appropriate probability distribution model, calculate an estimate for the probability that less than 3, Px is less than 3, of the next 10 shoppers make a purchase after entering a store. Okay, nice. N equals 10. And then P we've already been given 0.35. So our calculator can't do less than 3, but it can do x is less than or equal to 2, which is the same thing. So let's do that. Also, it's my first time probably properly using this new calculator. I'm just going to set up my light a bit better for you guys. May not look amazing, but that'll have to do. So we're going to go into the stat, distribution, binomial, CD, because it's cumulative up until the number 2, 10, 0.35. There could be errors while I'm doing this paper, by the way, guys, but I'm just doing a walkthrough as if I was sitting the exam, just so you can see. 2 assumptions made for the probability distribution model that you used in part I to model the number of customers making a purchase when entering a store. Is that bad English? To model the number of customers making a purchase when entering a store. Low key, I think we were using this to find a probability. Anyway, that's all good. I use fist for when I'm doing binomial, which is fixed number of trials, independent events. S is for same probability, and T is 2 outcomes. So we just got to pick 2 that we like. So I'm going to go, this one's quite general, so I'm actually going to try and avoid using the 10 shoppers. I'm going to go with the same probability. Every customer has the same probability of making a purchase, being 35%. Next one, I'm going to go for independence. It's a nice one here. I'm going to use that for number 2. Each customer is independent to other customers. Good assumptions to be made. Again, yeah, I'd like to apologize for the resolution. This is the best I could do for some reason on my camera today. I don't know why it's doing that. Anyway, question 3. The clothing retail company has many stores throughout New Zealand. Using an appropriate probability distribution model, calculate an estimate for the probability that at least 3 out of the next 10 customers make a purchase in each of the 4 different stores. Oh, nice. We found a grammatical error. Calculate an estimate for the probability that at least 3 Px is at least. Oopsies, wrong way. No, I did it alright. Px is equal. Yeah, nice. Oh, shucks. This is what would happen in your exam as well. The clothing. At least 3 out of the next 10. Okay, so this is the same as writing P1 minus P x is less than or equal to 2. And we already did that before, right? So it's just 1 minus this one. Nice. 1 minus 0.2616 equals 0.9 minus 2 is 7. 9 minus 3, 8, 3. I don't like how this question is written, actually. Calculate an estimate for the probability that at least 3 out of the next 10 customers make a purchase in each of the 4 different stores. So I'm assuming that 10 are going into one store, 10 in the next store, 10 in the next store, and we want to make sure that this number 3 or above is happening in each of them. And we're assuming that they're independent. Do they want an assumption? They don't even want that assumption. That's fine. So we're just going to do that, 0.7383, and then there's 4 stores. So we're just going to do it to the power of 4. Okay, this 0.7383 to the power of 4. 0.2971. I'm going to use 4dp throughout the external. An assumption was made. Aha, they do want the assumption. Independence of each store to the others. I'm calculating the estimate in part 3. Yep. Justify this assumption in context. Justify this assumption. So we're saying why it's fair in context. The stores operate independently of each other on a day-to-day basis. And we, oh man, that light is making such an annoying noise. I hope I can stop that for you guys. Man, this ends up being a real mucky video, eh? On a day-to-day basis, each store works independently of each other. What was I saying? And also customers independent from customers in other cities. Was it cities? And other, I'm going to say stores slash locations, because I don't know if that's like a, yeah, that's enough context. Let's move on. A particular store offers 2 alternative online ordering methods for items that are out of stock in the store: click and collect and home delivery. The amount of time until a customer's click and collect order is ready for collection ranges between 24 hours and 144 hours. We've given 2 values. For home delivery orders, the time for the order to be delivered can be modeled with a normal distribution, the mean 96 and standard deviation 38.4. 2 different distributions. 2 friends make online orders at the same time, one using click and collect and one using home delivery. I'm going to draw 2 pictures. We've only been given a maximum and a minimum, so 24 to 144 is for click and collect. What was the other one? HD. HD looks a little bit more like this, and HD is that 96 and standard deviation equals 38.4. Estimate the probability that both friends wait more than 120 hours. So we're given an x value here, x equals 120, and over here x equals 120. They want to know probability that both friends are more than 20 hours. So I'm just going to write it out. Px greater than 120. I'm going to call this x. Why not? I'm going to call this y. Woohoo! I'm going to get in trouble. And then we're going to multiply that by what happens with y. Y is greater than 120. So that's what we're trying to find. So those are pretty straightforward. What do we do for the height of the rectangular? I think this is b minus a. Does that make sense? Yes, because the base is going to be b minus a. Oh no, it's going to be 1 over that, and then it will get to 1 total. Yep. So we want to find b minus a, 144 minus 24. And we're going to go 1 over that. That's the height. And then the base is 24. I wonder if I'll get away with being that lazy. Yeah, I don't think I'll lose marks. I'm not going to show you my working out. You guys saw it, doesn't matter. Then we'll go to the normal distribution one. So we're just going to go distribution, normal, CD, always variable, lower is 120, upper is 9999999, 38.4 is our standard deviation, and the mean is 96. So probability is 0.2660. We're getting a lot of 0.2 somethings. Are they trying to play with us like that? Okay, let's just multiply them. Shift answer. Does that find my normal distribution answer? I think it does. No, it doesn't. 0.2660 times 1 over 5 is 0.5. Oopsies, I missed a 0 there. I'm going to do it like this. 0.532. Okay. Let's just see if we have... Yes, they got us within assumptions. I nearly did it. The stores, what are they called? The online ordering methods are independent, which is unlikely actually, because they're ordering clothes from the same store. So people working there, if they get an order for the first item of clothing, they're actually busy doing that, so then the second item of clothing will be slowed down. Independent of each other. Justify any assumptions. It's not even, yeah. Oh, that's 2 justifying of the same assumptions in a row. I don't want to justify it, because I don't believe it. What did they do? At the same time, they're not independent. Different teams will be working on each, what do we call these? Each CNC and HD or whatever. Anyway, question 2. Let's move. Management of the retail company have set sales targets of customers purchasing at least 4 items of clothing per 20 minutes in the store. Suppose that the number of items purchased by this company's customers per 20 minutes. Look at this. You see the per. Think poisson. Suppose in the store can be multiplied by with lambda equals 2.8. So calculate an estimate for that in any 20-minute interval a customer purchases less than 4 items of clothing. So we don't P X less than 4. This is like the most straightforward distributions exam I've ever seen. Less than 4 is the same as writing P X is less than or equal to 3. So X is 3. That's what my calculator can do. Lambda is 2.8. 69. Nice. Just double checking. What is this information for? Provide 2 reasons why these may not. Oh yeah, nice. A non-justify. Okay, I use Poisson for this. Alright, Poisson on the side. P, it's proportional. O, it occurs randomly or rarely. I is independent. S is simultaneous. Occurs never. May not. Yeah, okay, well, this is easy. When you purchase an item of clothing, you buy it all together. Clothing from a store is purchased at the same time. but simultaneous instances can't occur in Poisson distribution. But I've run out of space, so that's going to have to do. Reason 2 is independence good. You might buy matching clothes. Occurring rarely, it's a pretty good one to go with. And proportional. I'm going to go with independence, even though we've talked about it way too much already. Clothing items can be purchased, what do you call it? Sets in an outfit to match. Therefore, they would not be independent. I think the resolution's too crap and my pencil's too blunt. So this is probably looking rubbish. What other options have I got? This one's looking a bit better. Okay, let's keep moving. What would the value of lambda need to be so that under the Poisson model, at least 99% of this company's customers purchase at least one item of clothing in a 20-minute interval? So we're looking at the probability that you get 0 items of clothing is 0.01. So the probability of people buying nothing is 0.01. But then that's at least 99%. So I actually need to change that a little bit. Let me just get my head around it. So we're looking at Px is least one item of clothing. Greater than equal to 1 is at least 99%. So this is bigger than 0.99. So that means 1 minus that is equal to 0. People buying 0 clothes. I'm going to change my symbol around with a rubber. People buying 0 clothes actually needs to be less than 0.01. But how we're going to do it is we're going to use the Poisson. Oh shucks, I should have got a formula sheet. Can I remember it? Lambda to the power x, e to the power. Oh, maybe I can do it. P x equals x is lambda to the power x, e to the negative lambda over x factorial. I think that's right. Okay, that'll do. So we're going to go p x equals 0 is now less. I'm going to stick with an equals for now, and then we'll just mess around with it at the end. Lambda to the power 0, e to the negative lambda over 0 factorial. Everything goes away. This becomes 0.01, and we want that to be greater than what we find, e to the negative lambda. We could do we're going to take the natural log of both sides, and then I'll just do it slowly. ln of 0.01 is negative lambda, and then negative ln 0.01 and lambda. So look at that. ln negative ln 0.01. 4.6. 4.6 being greater than lambda. So lambda needs to be less than 4.6. Nah, that's wrong. I did something wrong here. Because lambda should actually... because I times it by a negative. That flips. This flips. So lambda needs to be greater than 4.6. Yeah, but don't worry, if you put lambda equals 4.6, you would have got that right. Just that at least is a little bit confusing. Okay, that's an excellent question. That's good because I spent a long time teaching my class that. So nice. Okay. B. The company receives their stock in boxes of 50 clothing items. The items are checked for defects before being sold. The table below shows the probability distribution of the random variable D, the number of defective garments found per box of 50 clothing items received by the company. Supplier A looks pretty good. Nice supplier. Use them. Fantastic, guys. Supplier B, get out of here. Calculate the mean and standard deviation of the number of defects per box of 50 clothing items received by the company from supplier A. Okay, we're going to do the table function. Go into stat. We're going to go in here and we're going to go 0, 1, 2, 3. That's our list. And then these are our frequencies. Let's see if this is set up right. Oh shucks. Calculate. Let's set the 1 var list 1, and then a 1 var frequency is list 2. Okay. Does that seem natural for 0.4? Is that? Yep, that looks right. And then let's go to oh shucks. I gotta remember which one that is. I think it's this. Let me see what else we got here. Yep. It's just the standard deviation next to it. Does that make sense? Yeah, it does. Okay. The clothing retail company prefers to receive boxes of garments with low numbers of defective items. Crazy. It is also helpful if the number of defective items per box is consistent over multiple boxes. Explains just reason to explain which supplier fulfills. So we want a low mean and a low standard deviation. We want low standard deviation for that consistency and low mean for the low numbers. So we actually need to go and do the frequencies of the other one as well. 0.66. 0.23, 0.07, 0.04, 1 var. So we're going to go supplier B has a mean of 0.49 and a standard deviation of 0. Oh, that's easy because both of them are higher. Perfect. Yep. So supplier A has a lower mean. I'm going to go mean A equals 0.4 is less than mean B, which is 0.49. So they have less defective items. Supplier A is also more consistent because standard deviation A equals 0.7348, which is less than standard deviation for B, which is 0.7937. So the number of defective items is more consistent, lower standard deviation. That's enough. Let's move on. We up to the next question? Oh, we're nearly there. We're 2/3 of the way, guys. Okay. The retail company collects data on the amount of money spent by each customer in one visit to a store. So we've got N, we've got mean, we've got standard deviation, we've got mode, and we've got max. Interesting. It is claimed that over 25% of transactions consist of spends of more than $150. Here's $150. So we're looking at this area. Is this claim correct? What is N? N equals 100. Now, I'm going to do a little table real quick. 150 to 175. How many? 1, 2, 3, 4 things. Okay. How many? That line is at 19. And then 175 to 200. That line is at 10. Then 200 to 225. That line is at 3. 225 to 250. So let's total them up. 20, 30, 33. 33 over 100 is greater than 25%. Is this claim that over 20? Is this claim? Yes. In fact, 33% of the transactions in this sample were over $150. Now, just quick little extra thing. Low key, people that spend $150 could be falling in here or could be falling in here. So we can't actually answer this because money spent is likely to fall at maybe the 150 because this is not actually a continuous distribution. You can spend $150, so I don't know which thing that falls into, but they don't care to know that. Next question. Use a normal distribution model to estimate the probability that a randomly chosen customer spends more than $150 in one transaction. We've got a mean 127.75, and what was the other one? Standard deviation 46.22. We're going to go to normal distribution. This is the easiest. Distributions paper I've ever seen. So lucky you guys if you got to sit this one, but maybe they'll make it. Yeah. Px greater than 150 is equal to 0.3151. Yep. Suggest an alternative model that could be used for modeling customer spend per transaction at this particular retail company. Triangular. Is that what they're going for? We've got a mode. We've got a max. But what's the min? 0, I guess. Yep, look at that. We've got that. State the parameters. Min equals 0. Max equals 250. Mode equals 130. What else are we missing? Triangular distribution. Yep. Use this alternative model to estimate the probability that a randomly chosen customer spends more than 150 in one transaction, given that they spend more than 130. I like it. Okay, mode is slightly to the right of the middle. it's 2 over b minus a, right? 2 over 250 minus 0. 1 over 125. Is that right? Yep. Middle is 130. Oh my gosh, it's so easy. They gave you the number that's the mode. Oh, you are lucky duckies. But 250 there. What is it? There's a 0 down there. That is crazy that you're getting these. So they want to know that probability given you're in this probability. What are we going to do? We're going to find the total triangles area first, and then we're going to find the mini boy one, and we'll just do that over that. 130 to 250, that's a distance of 120, height of 1 over 125. That's nuts. Okay, this height's a little bit nicer to. I need the calc. Oh, I'm gonna need a formula sheet. Could I use some tricks here? Nah. The NCEA stats level 3 formula sheet. Dang, I thought I could get through without it. Okay, so this is between C and B, right? So we're going to need 2b minus x over b minus a, b minus c. Double. Just let me get that so you can see it. Okay, 250 minus 150 over 250 minus 0, 150, no, it's B. 250 minus C, 130. Let's do it on a calculator. Big old fraction. 250 minus 150. Take me downstairs. 250. We're going to do the full thing even though I don't need to. 250 minus 130. 1 over 150. That is the... what was that? That's the height, eh? That height is less than that height. Good. 1 over 150, and the length is 250 minus 150, that's 100. Okay, I've got two triangles, let's find their area. 1 over 125 times 120 times 0.5. The area is 0.48. This next triangle, 1 over 150 times 100 times 0.5. 0.3333. So it's 0.3333 over 0.48. But I'm going to go more accurate just because I can. I've already got it in my calculator. I'm going to go shift answer divided by 0.48. 69. I think these guys are intentional here. That's what I'm saying. 0.6944. We found the probability of that out of that. Yeah? Yep. Next question. Two more questions. Compare the probability, your probability estimates using the two different probability models with your probability calculated from data in part A. Which model gives the closest estimate of the probability that a customer spends more than 150 in one transaction? But the thing is, we were finding some conditional. Which model gives the closest estimate that a customer spends more than 150? They're the same! What? No. Oh, wait. Models, sorry. I was comparing this 33 out of 100. So 0.3151. So normal it says px is greater than 150 was 0.31. Man, my brain just can't remember digits like that. 51 triangular px greater than 150. The thing is, we weren't even actually calculating that. That was part of what we were calculating. 0.33. I'm just going to write it as 1 over 3, guys. My bad. Which is 0.3333. Which model gives the closest estimate of the probability that the customer spends more than 150 in one transaction? What? 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 Ugh, I don't know what they want. Do they want me to talk about comparing it to this number here? Because this is not normal. This is not like a normal distribution. It's got a left tail. What is the mean? 127.75. It's like somewhere here. What's the mode? 130. Oh, guys. Oh, I don't know. That's matter of opinion. Triangular is closer to the sample data, but normal seems to model the shape of the sample data better. Triangular. Because I think they're asking closest estimate. I don't know. I don't know if I'd agree with that. I kind of prefer the normal. Recommend which model normal distribution which should be used for modeling the spend projection in this particular store. Okay. I prefer the normal distribution. But the sample data is left skewed. I remember SCAM for normal. SCAM. S being symmetrical. C being continuous. A being asymptotic. All of these actually. And M being mostly around mean. And also remember that mode equals median equals mean. So we want to find we want to try and justify though. So we need to find the good part. So continuous is good, but the continuous is the same as triangular anyway. And asymptotic is actually low-key bad. Symmetrical is low-key. We've shown that it's a little bit off. But we can probably talk about mostly around the mean. Spending is pretty much, it's not quite even, because continuous data and the data is mostly whatever around the mean. Okay, that's it from me. I can't, yeah. So that's what I did for the 2022 exam. I've been your host, Mr. Forbes, and yeah.